So as you see here, we have a group photo of everybody, just after the lecture. So don't leave lecture. It's 5 minutes to take the photos and so on. Okay. So today we will continue our discussion of between species, and we will focus on competition. So competition, as defined yesterday, was interaction such between two populations, and such that this interaction is detrimental for both populations. Detrimental means the interaction tends to decrease the size of the populations. It's bad for both of the populations. So we will build a model. Build a model for that, interpretation and examples. First of all, there are many underlying biological mechanisms that are connected to competition between species. So, and the main classes could is exploited. Both species compete for a limited resource. So, exploitative competition is a mediated interaction. Okay? It is not like dynamics. Predators actually feed upon their prey, something that you can go and say, I see. So for exploitative competition, you actually don't see competition at the level of the individuals. Competition exists at the level of populations in this case. Right? So this means that this is not, if we describe without talking about the dynamics of the resource, then this is not a mechanistic model, because it is not based on what individuals do scaled up to populations. Okay? So, but exploitative competition is the most widespread form of competition. Actually, different kinds of exploitative competition. You have situations, and this competition can be intra-specific between the individuals of the same species, of the same population, or between. Okay? So usually the exploitative competition is divided biologically in or contest. Scramble competition, I have a certain resource. Say I have 10 units of my resource, and I have, say, 100 individuals. Scramble competition means that every individual will get 0.1 units of the resource. It will be divided. Okay? Typically, what would you say? Interspecific competition of cows for grass. Okay, that would be the textbook examples. Okay, and in the other case, the context is different. You have competition between species or interspecies, and a subgroup or one of the species wins, say, the competition. It's like the winner gets it all. Okay. So I have my 10 units here, of resource. I have 100 individuals. 10 individuals will get 1 unit, and 90 don't get anything, for instance. Okay, so this is contest competition. So we will not make a differentiation for our models here today. It is possible to do this, and it is done usually in the context of discrete time dynamics, where you have different models for scramble and for context competition. We won't make difference here. We will just talk about exploitative competition. So, exploitative competition is not the only competition that exists in the world. There's also interference competition, where one species actually actively interferes with the other species, but it's not a consumption. So the typical textbook example would be territorial species. Okay? So I have resources. The species is such that the species avoids other species to enter this territory to get the resources. Okay? So they go there and puff, get the other out of here. Okay? So it defends the territory. So this is in the case of interference. But it doesn't consume. Okay? So as it doesn't consume, it just spends energy defending. Therefore, it's detrimental for it because the energy is not put into reproduction or whatever. And it's also detrimental for the other one, which does not get resources. Okay? So it's competition, it's not consumption, and it's by interference. We will not models directly for interference here. Okay? Anyhow, you will see the models for competition in general, and then at the end I will tell you a little bit of what would be a different way of proceeding. Okay? Now, you could talk about two kinds of models. One model, which you could do implicit or phenomenological, are models that take into account the dynamics of the resources. We will have an implicit model means that we will talk about population 1 and population 2, which compete. They compete for a resource, but the model will not be for the resource. The resource will not be in the model. And you could have different models. That's I will comment at the end of our discussion today, which would call explicit models for competition, which means that you will have one species 2, but you also have the dynamics of the resources that are being under competition by the species. Okay? So there are typically two kinds of models. The first one is the kind of what people would say competitive Lotka-Volterra models. Okay? And the explicit one is what people call consumer resource. So we will go for the simplest case. There's two species, no resources taken directly into account. But we have two species, we will have competition intra-species. Each population has the competition between their own individuals, and interspecies, between the two species. So that's the ingredients that we want. We want to build a model with two populations, specific competition, the goal. And then to analyze this, they will have a little bit more mathematics to analyze this about qualitative analysis of differential equations. But the main goal is this this kind of model now. Okay? Very good. So we will proceed in a way which is analogous to the way we proceeded yesterday for building the predator-prey dynamics. So we need two species. I will use N1 and N2 for species 1 and 2, which are function of the time. Yeah. So again, two equations, two coupled equations. And I will build step by step as yesterday. It will be quite easy. So I will suppose, my hypothesis is that species 1 and species 2 both grow logistically in the absence of competition. So if they are isolated, then they grow logistically. Okay? So species 1 has a logistic equation here. Species 2 has another logistic equation. Intrinsic growth rate R1, and this is different from species 2, R2. And each of the species also has a carrying capacity. Okay? So this is without interaction. So what we did yesterday was introducing interactions by putting a term here on this N1, say, something here which depends on N2, and something on this side of this equation which depends on N1, which describe the influence of N1 on N2 and vice versa. Right? So, and we will working, yeah, yeah. It's, so the simplest one, putting making the simplest choice, which is that. Okay? You have the species 1. You have a logistic equation here, and you put a term here with a minus sign, which describes the influence of N2 on N1. And here you have a also sign, the influence of N1 on. You see, yesterday we had something very similar, but there was one positive sign and one negative sign. Now it's both of them are negative. So this is what, because it's describing competition of equation on the other, on one species on the other. So again, so this is important, so maybe I should do this a little bit on Blackboard. What you have is, if you write again this, which is, this is the rate of variation of the species 1 per capita, okay? And this is R1, okay? 1 minus N1 over K in the absence of competition. So that, in this is the per capita rate. I'm saying that the species number 2 has the effect to decrease this growth rate, per capita growth rate, in a linear way. So I just put something here. I could put it outside, but just minus N2. Okay? So it's linear and simplest choice. There could be other choices and so on. This is the simplest choice. Okay? And it's such that we will be able to make the qualitative analysis of this dynamics. Yeah. Yeah. Species 1 and species 2 are limited by some resource. So there's a jargon about limitation. So this is a bottom-up limitation. Okay, yesterday, so bottom up is the resource limits the growth of your populations. And usually then you say if for instance, prey is limited by the predator, if it's limited only by the predator, this is top-down regulation. So you can have top-down or bottom-up. So there is, these populations had, there's some resource. This first mystery, right? Mystery. Where's the, what are they competing for? So this is what people call a phenomenological, non-mechanistic model. Okay? The resource is not being modeled. Okay? So ask, isn't that strange? Right? In some sense it is, because I'm just modeling the influence of population 2 on population 1 and vice versa. But there is no real mechanism being modeled, because yesterday the influence of, say, the predator on the prey was clear. I mean, the influence is because he consumes the prey. Okay? So here, this is not being modeled. There's no explicit model of what the competition is for. So it's a kind of mystery action. Population 1 is here, population 2 is there, and somehow they have an influence that is detrimental for both of them. So it's not a direct influence. It's mediated by resources, of finite resources, obviously. The strength of the competition depends on the amount of resources you have. So, and all of this has been, all this process of consumer resource dynamic has been so thrown away from the model, and what you get is the effective influence of 2 on the growth rate of 1 and vice versa. Right? So that's a phenomenological model. It is not a mechanistic model. Okay? No. Because in this sense, you cannot see the competition. It's not a direct. See species 1 consuming its resource, which is shared resource with species 2. And these are the mechanisms, but they are not being modeled. What you have is only the influence of 1 on 2 and of 2 on 1. I just on the board very briefly at the end. That you can. The point is, this is also of the art of modeling. Okay, art of modeling has many things. So you say, okay, I have population 1, I have population 2, and both of them consume the same resource. Great, you can do this. Actually, people do this. It's called mechanistic competition model. Might have another resource. Or maybe it's not the only resource. Maybe you have 2 or 3 resources which are shared to a certain amount by species. And you have to cut this at a certain point, because you don't want the whole trophic network. Okay? And so where do you cut it? Okay? Where do you say now? I have to, somehow, I cannot go mechanistic all the time. Okay? I will have, there is some point where the resource, I will have to say now, okay, this one here, I will model this as just a logistic, and I have to put, because otherwise I have to pull 100 species all the time. Okay? So this is kind of art also, like, okay, let's take into account only the two competing species, and the next step would be take 2 species and 1 resource. That would be the easiest next step for modeling. And this can be done, and it's not difficult. It's in the textbooks and so on. And you can take 2 species and 2 resources, and then you can find the consumption rates, preferences, and all. You open up a whole new world of consumer resource models. Okay, so these are the equations. Now, we will spend a certain amount of time trying to analyze these equations, okay? So you can see this as a step to obtain the results about these equations, but you can also see this as an exercise in how to do qualitative analysis of differential equations, of 2 ordinary differential equations, okay? So there are some steps. All the calculations, actually, this would take time. A little bit like you have to calculate what's called Jacobians and so on. It's not part of the course. So we want to extract information from these equations. I think is to write. I wrote here, for instance, I put some A here. Okay. Now A is arbitrary at this point, okay? It's just a proportionality constant. So if it is arbitrary, I can just write this arbitrary constant in terms of another arbitrary constant, just because I like it, okay? So I will say A, constant, which are called B, 1, 2 over K1. K1 is the here. And B, A was a constant, B is a constant, okay? There's no, you don't have to try really to give biological interpretation to this concept at this point, because this is a phenomenological model. Because, anyhow, yeah, just the influence of one on species 2 and vice versa, and this is some proportionality. How do I calculate this proportionality constant from the? You don't do this because it's not mechanistic, it's phenomenological. So I A, now I want to call A B. Change the name of the constant, okay? And if you do this, you obtain equations that are on the slide. Okay? Why am I using this okay? So, okay, this is the usual way that this model is. That's Lotka-Volterra competition model. Okay, Lotka-Volterra-like. It's built like a Lotka-Volterra model. Okay. Okay, so you have 2 equations, and now we want to see what do these equations tell me about? What are their solutions? Are there solutions? Again, there are trivial solutions on which are constants, but the dynamics, the real solving these equations, it's not possible. So we will have to resort to our 2 possible ways of analyzing things, which are numerical or qualitative analysis of differential equations, and we will do the qualitative analysis here. Okay, so and I will just start with playing with the names of the variables. Okay, so I have variable. The variables are n1 and n2, okay? Yesterday, I noticed that people sometimes make a confusion between variables and parameters, okay? So in this equation, for instance, the variables are n1 and n2, which is the unknown functions of your equations. And the parameters are that's the thing, right? So these are parameters. Parameters be time dependent in principle, yes, but are given things, okay? Like yesterday in the final discussion of Renato, he had some seasonal rate, okay? And but the main differences between what are the unknown functions and what the rest are the parameters, okay? So, okay, I will start to play with these equations, with the substituting things, because I want magic. And the magic I want is that two equations. How many parameters do we have? 6 parameters, okay? No, 6. 1, 2, 3, okay. We have 6 parameters. So our parameter space has dimension 6, which is already starting to be a little bit too big, okay? Because, you know, we want to explore the dynamical behavior of the equations in terms of the parameters. If the maybe there are different behaviors, different coexistence or exclusion of species, whatever. So, and you see, now many of your group works have not only 2 equations. I mean, I think everybody has at least 3 equations in the models. Yeah? And if you put a third one, you see the multiplication of parameters, okay? So you would have 12 parameters in this case. And starts to grow and grow and grow, which is called the hell of the parameters, okay? The hell of this is you have too many parameters, and the main point is when you do modeling, I'm not talking necessarily about these equations, in general, parameters are okay if you know their value, okay? If you know their okay, you're putting realism into your, but unknown parameters are a problem. What do you do if you have a model which has some constants or some parameters that you don't know, that have not been measured, but they are in your equations, and then you want to compare your equations to data or to something that you see in nature, okay? What will you do? You have to fit the parameter to the data. Fitting, okay? Now, if you have a lot of parameters, you have a lot of liberty for fitting, you fit anything. And your model has no value because it can explain everything that happens. A model that explains everything, because you can't go on playing with the parameters, is a non-predictive model, right? That's useless, okay? Cannot make any prediction in the sense that whatever you see in nature or in the lab can be explained by parameters if I choose can be explained by my model if I choose the parameters. The parameters explains everything. Okay? This is a useless model. So you don't want to have a lot of parameters. If you have, maybe you can fit with only one parameter, okay, this will give you predictability. Say we have one situation, and that you use to fit the parameter, and you want to look at the same value of the parameter that you have fitted, and then you have some. Okay, this is how things should go in the analysis of data and theory. Okay, this is also at the very basic steps of data analysis and what people call machine learning, things like, okay, if you have too many parameters, you get precision of the fitting, but you lose predictability. If you have few parameters, you have less precision of the fitting, but you can get predictability. If somebody interested on that, after the class, we can talk about this. It's not a problem in ecology, so I don't want to go on this, but I can show you on the blackboard after the class. So therefore, I hope I've convinced you that we don't want too many parameters. And this is, pay attention for your models, okay? Because, see, you want sometimes to put realism into the models, but usually this means that your equation has some new term or some new variable, and there will be always some parameters around. The value of the parameter, you have the range of values possible, or you have an educated guess of the value of the parameter, then it's okay, because you know, then it's easier, but parameter can be anything. This is not good. And if you have too many parameters, your model is so. Okay, so we have 6. And now I will show you that we can have less than 6. Isn't that line? That's in line what I told you. We don't want parameters, so I will just get rid of some parameters. This is fantastic. So pay attention to the magic. I have two functions, N1 and N2. I can, because I want to define new functions, which are the old functions, divided by their carrying capacities. Okay? So if you want the interpretation of the new function, the U1 and U2, is the population of species 1 compared to its current capacity. Okay? And the same thing for population 2. It's the population 2 compared to the carrying capacity of K. This would be kind of non-dimensional. Okay? This is a pure number. It's not a dimensional. And I also have the time. So I will just say I have time t1, okay? And I would like to have a time, a rescaling of the time. So let me rescale the time and say that time t1, t1, not t, right? Only time t. I will multiply time t by r, and now remember, recall that yesterday or day before yesterday, I told you what is the dimension of the parameter r was 1 over time. Okay, so this is time multiplied by something which is 1 over time. Therefore, this has no dimension. It's a dimensionless time, and I call it tau. Here we are with tau. Okay? Now, I take this and I put this into the equations. Okay? So where I have, for instance, I want to do all the calculations, but say I have dn1 dt, I will have g of u1 times k1 divided by d of t is equal to tau divided by r1, okay? which will give you K1 times G1 d tau times R1. Okay? This term. I'm just showing this term, but the other ones is the same. Okay? So just substitute. N1 is U1 times Q1. And Q1 is a constant, therefore it gets out of the derivative. T is times tau divided by R1. R1 is a constant and also gets out of the derivative. So it gets here. And then you get d U1 d tau here. Okay? And we will find equations for U1 and U2 in terms of the parameter tau. Okay? So we are just substituting scaled variables. All the U1, U2, and tau are rescalings of the original parameters. Yeah.
I can find a reasonable interpretation for the U variables is just a proportion. I mean, the train capacity software. But what is a time variable without units? What is the feasible interpretation?
You're counting the time in units of the R1. Okay, so this gives you dimensionless time. I mean, you can put anything without dimensions if you have a scale. There's a typical time scale here, and actually R1, R2. It's arbitrary. I used R1, but I could have used R2. So I have a scale, and I can measure my time in the scale that I have in the problem. So this will not be very important because we will look for the long time behavior, right? Okay, so therefore, now you do this algebra. You substitute U1, U2, and tau. You put this into the equations. You do the algebras, okay? And when you do this, you end up with this equation. Okay? So I'm not making a calculation here, but this is the equation for U1 and U2 in terms of the variable tau. Then you get these things here. Okay? And now I will give new names to the combination of parameters I have here. You see, I have combinations, R1, R2 over R1. Then I have combination, which is K2 over K1 times B12, and here there are other combinations. So I will rename these combinations, and I will use these names, and I get this system of equations, which I want to analyze, which has 3 parameters. We had 6, now we have 3. Magic. So this is very nice because just by renaming things, I'm rescaling and renaming the functions, I just ended up with less parameters. Okay? So this seems magic, but it's obviously not. I mean, you had 6 parameters. You had 2 variables and the time. So you could rescale the N1, N2, and time. This gives you 3 things, okay, possible. And you have 6 minus 3 coming from the rescaling. You end up with a combination of 3 parameters. You can do this in many situations, okay? And you could be a little bit bothered by this. I had a system. This is supposed to describe a system of competing species. I had a 6-dimensional parameter space. And now I have a 3-dimensional parameter space, but what's the good dimension? you could say it seems arbitrary, but it can't be arbitrary. There were 6, and now we are 3. So the parameters seem to, the dimension of the parameter space changed. So there's no problem about that. Why? You see, what I'm showing you with the final form of the equation is that although you have 6 parameters, it's only 3 combinations of these parameters, which were in the previous slide. Oops. Here. It's only this combination of the parameters that matters. So you have 6, but it's only the combination that matters. Therefore, oops. Therefore, you had a 6-dimensional parameter space, but what matters for the equations is only a subspace of dimension 3, if you want to put this in mathematical language. Okay? So when you want to study the equation, you don't need to explore the 6-dimensional parameter space. You can explore only a subset of the 6-parameter space, which are the combination of these parameters. So this makes a kind of hypersurface in the 6-dimensional space. Okay. Yeah. When we saw the solution, you mean? Yeah. U over time. It's the population and time. U is the size of the population with respect to its carrying capacity. So it's just the total amount of the population multiplied by a number. Okay? Okay, you would say, okay, I now want to go for data, which in data are not, they have cows and, I don't know, something else, okay? So, and I can count them. I don't want to, I have the hours. Okay, so you say, for instance, I have cow time, and here I have U, and there's something going on here, okay? So, but U1, say. But you know, U1 is just N1 over K1. So you go on this, and you just take this and divide it by K1, you get a new thing here. Just the actual, you can get this one to this one. And the time, the same thing. You just multiply the time variable by a constant, which is, and that's it, okay? So you can convert between U's and N's and time tau. It's just a matter of multiplying by a number, okay? Hmm? Good, okay. So, it's a very good question, and so, how do you obtain the parameters? K1 and K2 are phenomenological parameters. Different from R1. R1 or R2, the growth rate. I can take the population. I could do an experiment and isolate the population, and then look and calculate the growth rate. A small population growth rate, I can get that one, and this is independent of N2. Okay? So you can actually find this in an experiment. We are not talking about field, because then there are different things, and I will comment also on that, but let me first get the results. But now, if you would like to have the carrying capacities, well, then you would have to make first a controlled experiment, also N1 isolated, and see the growth up to a certain point, and how this depends on the amount of things. Then you could get this. What you cannot get is the interaction parameters B1, B2, because in order to get them, you need to do a competition experiment. okay? And fit B1 and B2. B1 and B2 will always be fitted. And that's the problem with this model. It's, we come to the glory and misery, and the misery is this. Okay? So it's non-predictive. But although it's non-predictive, we will get very nice result off of it. So, okay. Wait a minute. So we want to study now the behavior of the solutions. And here, welcome to qualitative analysis of differential equations. We will look first for the fixed points. So again, I talked about this yesterday, but it's, you know, repetition is the basis of education. Okay, so I will repeat a little bit what I told you yesterday. So I have the questions, and I can now. Obviously I will be interested in the U1, U2 plane. Okay, and the curves here will describe the solutions graphically. It's a graphical representation of the solutions. Okay? And so, first thing is, are there special values of U1 and U2 such that if the populations have these values, they will continue to have these values forever? Therefore, the time derivatives are 0. So we will look for the fixed points. Okay? So let's look for fixed points. Okay? So fixed points mean we will put the time derivatives equal to 0, which gives you these two equations, which are algebraic equations between U1 and U2. And now this is understood here that this U1 and U2 are the special values such that the solution will be constant. There's no time variation. Okay? So, and it is easy to solve this system of equations because they are quadratic. Okay? It's actually here the maximum. You have U1 times U2, and the rest is U1 squared. The other terms just U1. These are two quadratic equations, okay, and very easy to solve then. Right? So that's the special thing about the model I'm building. I get polynomial equations, which actually can be solved. Okay? Now, if you had more species, you could do the same analysis again. Why not? Fixed points and so on. But you would have more functions. It will take you to higher order polynomials, which you probably would not be able to solve, okay, explicitly. Okay? You got a fifth order polynomial. No way. Okay? You do graphical solutions and so on. You can proceed and so on, but the analysis I'm showing here is really simplified by the fact that you can solve explicitly these polynomial equations. So they have 4 solutions. So a solution of this system of equations are pairs U1 and U2 of constant value, okay, which are solution to the equation. So these are clearly this one. So U1 could be 0, okay, which would, if U1 is 0, it's this one, this first equation is guaranteed to be satisfied. U1 is equal to 0 here. Then you can have either U2 equal to 0 or U2 equal to 1. Okay? So you have U1 equal to 0, U2 also equal to 0, or U1 equal to 0 and U2 equal to 1. And, well, you can do the same thing, finding a solution such that U2 is equal to 0. This one is satisfied. And then this one is satisfied if U1 is either 0 or either 1. Okay? So it's a way to satisfy this equation. So it's very easy. so these are the three solutions, and this one comes from saying neither U1, neither U2 are 0. Both are different from 0, and in this case, I need this thing here to be 0 and this thing here to be 0, which are two linear equations for U1, U2, which you can solve. It's a system of linear equations, okay? So, and then you solve it, and it will give you this here, okay? So these are the fixed points. So these are the values of the population such that if the population has these values, it will not be variable, okay? So what do they mean? Well, the meaning is obvious. This is mutual extinction. No population at all. This is zero population. This is, here is, the second one here is the population Q got, U2 got value 1. But it's, what does it mean? U2 is being measured in terms of the carrying capacity K2. So being 1 means U2 has the value of its carrying capacity, K2. And population 1 is 0. This is the same story, just changing 1 to 2. And this is coexistence of both populations. So you have three, you have one is this mutual extinction. This one is coexistence, and these two are the elimination of one population in favor of the other. So one, this is the it's one population has prevailed, okay, and eliminated the other one. Okay, so these are the fixed points. But now comes a point which is very important, and maybe people have mathematics and physics have seen this. Depends. That's a little bit of your mathematical education. The point is, you'd say, okay, but this doesn't tell me anything at all about if I start somewhere else, not on the fixed points, what will happen to the solution of the equations? No guess. So, to discuss this fully would be beyond what we would like to make here, but we can start by discussing the stability of the fixed points. What does it mean, the stability of the fixed point? The stability of fixed point means, say I am on a fixed point, and I perturb it by an infinitesimal perturbation, as small as you want. Will the solution go back to the fixed point, or will it drift away? So if I have a fixed point, and I make a perturbation, and the solution in time goes back to the fixed point, I say that the fixed point is stable. If the fixed point is perturbed and the solution drifts away, it's unstable. Okay? So, fixed points that are unstable are in practice non-observable. They don't exist in nature because we are always under perturbations. So if your fixed point is unstable, it's the same thing as saying, okay, it's a property of your equations, but it's not observable because you always have some small error in anything. There's no such thing as infinite precision in real systems. There's always some precision. Means that there's some small error in your data, and therefore, if your fixed point that you calculated turns out to be unstable, that means that you will never see this fixed point. Okay, so that's it. Okay, the classical example of fixed points could be a pendulum. Okay, you got a pendulum here, which can, like this. You know that if I put it here, and I perturb this, and there's some little bit friction with the air, then it will go back to this point. But there's another fixed point, which is it's the upside down pendulum. Okay? You don't see this, yeah? Because any perturbation takes it out of the fixed point. Yeah. Infer. You could infer, yeah, this could be, okay. You could infer the existence of unstable points. It is possible. It's not observable in the sense that you don't see them because it's unstable, but you can, in certain circumstances, infer the existence of unstable fixed points. That's true, right? Okay, here's one case here is the 0, 0, okay? 0, 0 is there's no populations, and in the practice you would say, okay, if there is no population, I observe it because there's no population. Because actually that's a very singular case where maybe you are not perturbing it. But if you introduce a little small amount of the population, it will grow. So, therefore, it is important now to say, no, if the fixed points that I obtained, are they stable or not? That's the question. Are they stable or not? So, the result will be, it depends on the parameters A1, 2, and A2, 1. It will depend on the parameters. Depending on the value of the parameters, you will have stability or instability of the fixed points. Therefore, I have to analyze each fixed point and see if it's stable or unstable depending on the parameter values. Okay? So, there's a way, which is not mathematically very involved, but it's a lot of calculations. I will ask you to believe me like a priest. Okay? I'm telling you the result about the stabilities. How do you study stability? You say, I take my value U1 to be the fixed point, plus some small increment, which I will call, I don't know, delta of t, which is a function. And then I substitute U1 as the fixed point plus some small increment into the equations. And I look if the equation for delta give you increase or decrease of delta. If delta decreases, means that over a longer time, you will get close to U1. If delta, I say it correctly, yeah. If it decreases, then you have the stability of the fixed point, because the perturbation is getting smaller and smaller. If delta increases, then you are drifting away from this value, and therefore the point is unstable. Okay? There's always the possibility of having a delta equal over the time equal to going to neither increase, neither decrease with 0. It's called neutral stability, but we won't discuss this here. Okay? So that's the calculation that you have to do. It's a matter of doing calculations and putting these things into the equations, and using some tricks like linearization and so on. But okay, you see that there's no time to give you all of this calculation here. So I hope you understand what is stable and unstable, and I will give you the results of a calculation that you can do about the stability of the fixed point. So let me just, yeah. The result will be the following. Everything will depend on the values of A12 and A21. No. No, we have 4 fixed points. One of them has coexistence. 2 of them are exclusion of one species in favor of the other, and the last one is mutual exclusion. So I want to know, for instance, you can think of invisibility. I have a species, say species N1 is on its current capacity, living here and being happy. And then there's a small amount of species 2 arriving. Okay? So if the fixed point is stable, species 2 is a perturbation of the fixed point N1 equal to its carrying capacity. So if this fixed point is stable, means that N2 will not be able to invade. But if it's unstable, means that N1 will go away from its fixed point, and N2 will get some value. Well, the long time behavior I'm not talking about, but so it's about the importance is to know if you can observe that if it's not stable, you can't observe. But you also can think about an invisibility. Okay, you can think I have species 1. Can it be invaded by species 2? And I have species 2, can it be invaded by species 1? Usually this means the final result of this is if I have species 1 and can be invaded by species 2, but species 2 is not invaded by species 1, will mean that species 2 will prevail and eliminate species 1. Only if you have mutual invisibility, 1 invades 2 and 2 invades 1, then you will have coexistence. So, but I mean, I'm getting already so more. I won't show you the invisibility analysis because. Anyhow, so it is important that a fixed point should be stable, so that what I predict about the nature should be observable. Okay, so it's like the pendulum. Okay. There exists this point here, which is unstable. Well, you never see it. Okay, you never see it. So the prediction of the dynamics of this pendulum is that it will, at the end of the day, be here, not here. Okay? And that's what you see. There is a fixed point. Yeah, there is, but it's a mathematical property. It's unstable. And if it's unstable, then you won't see it. And this is the same with your populations. It's just different equations and different meanings. It's not a pendulum. We have two populations, 2 functions, fixed points, and I will only observe the ones that are stable. Okay? So, in order to know which ones are stable, I have to do this analysis that I skipped here, and the result will be that if both of them are smaller than 1, this one is stable. The fixed point of coexistence is stable. If A12 is smaller than 1 and A21 it's bigger than 1, then the population U1 goes to the carrying capacity and U2 goes extinct, which is this fixed point is stable. This is a stable fixed point. This fixed point is the elimination of species 2 in favor of species 1. It is stable in this case, and we will get an interpretation for these inequalities. So in this case, remember, A21 measures the influence of species 1 on the species 2. And it is bigger than 1. So we'll say it's strong. While this influence of species 2 on species 1, which is given by this first here, is smaller than 1, means that the influence of 2 on 1 is smaller than the influence of 1 on 2. And at the end of the day, this will lead to the stability of the fixed point, which is this one. So if this one has just change in 1 per 2, which A21 is bigger than 1, A21 is smaller, then you get the stability of the fixed point, which is the elimination of 1 in favor of 2. And if both parameters are bigger than 1, then you have 2 possible stable fixed points. There are 2, which is always the elimination of one of the species. So, summing up,
Biologically, what's the situation represented by the non-trivial stable point?
this one,
No, the non-trivial, the one that involves
this one.
the A. Yeah.
This is coexistence of both species. So, I mean the following. We will look, I didn't make the all analysis which you see. We would like to know, given our initial condition, what will happen to the solution. Okay, this is called global stability analysis, which we won't go. Okay? But as a result, you will obtain that, for instance, here, with these conditions, that's the only fixed point, means that the large time behavior of your solution, which can start anywhere, after a long enough time, will tend to this fixed point, will get this value, which means that neither population 1, neither population 2 are 0. So they coexist. You go to the field, you see population 1 and you see population 2. Even after a long time, in this case, you have both species coexisting. So, these other situations, there's always one species that outcompetes the other one, and you get the elimination of one in favor of the other one. Here, this is a case when the competition is not strong, because you see these inequalities here. The competition is not strong, then you can have coexistence. So there can be a lot of discussion about this, because this, as I told you, is a phenomenological model, and what is a smaller, because all of this has a little bit of tautology. What is competition not being strong? Okay. It's these values of these parameters, but these parameters are also arbitrary constants. So competition not being strong means that you could say, okay, that it's not strong when species can coexist. But I mean, this is the result, and so you are being tautological. Okay? This one? So, no, not random. So the good question is, okay, I have stable point here and here. And I know, because God told me, that the dynamics is such that you will get a fixed point at the end of the day. Which one? Will depend on the initial condition. Okay, you will see it on a plot in a few minutes. So, in principle, you could say, I don't believe you. I think that this is a planar system, and you could have periodic orbits as well as fixed point. It's true. There's a little bit more mathematics that you can use to show that there's no limit cycle in this case. Okay. This is an application of Poincare-Bendixson with something else. So it's not, but it's not so trivial, okay? You use Poincare-Bendixson theorem to prove either fixed point existence, because sometimes you can show there's no limit cycle, and this is a planar system. Therefore, the only possibility is either escape to infinity, but maybe you can show that there is no escape to infinity, and then you have a fixed point, and vice versa. Sometimes you can show that there is no fixed point, which means that if the system is bounded, it will go to a limit cycle. Okay, so that's the use of Poincare-Bendixson, but this is particular to dimension 2. Okay, just remember. So you have this stability results. So the intuition is the one that what I was telling you, that the A1 and A2 measure the mutual influence of the species, and when compared to the value 1, because they are non-dimensional variables, then you can have either stronger influence of species 1 on species 2, or stronger influence of species 2 on species 1, and so on and so on. So if I now draw this fixed points in the phase space with U1 and U2, this is the fixed point of coexistence, which I can show here better. Okay. These lines here, I don't want to discuss the lines because, I mean, we will run out of time completely, which are null lines that are the, but don't look at them because we are not doing the full analysis of stability analysis. But this is the fixed point. And I told you that this fixed point is stable if these parameters are smaller than 1. Okay? So this represents the coexistence, and actually you can show it's a global attractor. I can start anywhere on my phase place that after a long enough time I will be very close to the fixed point. So this means this is a situation of coexistence. Here, both of them are bigger than 1. So here is the fixed point, which is the coexistent, but it is unstable. And then you can ask the question that she asked before. Given initial condition, where will I get at the end of the day? So I have 2 fixed points, which are stable, which is this one and this one. This one represents the outcome that species 1 outcompetes species 2, and this one says that 2 outcompetes species 1 because of they are on the axis. So then I want to start at a certain point. Where do I get? So you can get either here or either here, depending on the initial conditions. So there are points in the phase place that will go to this attractor, and other points that go to this attractor. Okay, that's called a basing of attraction of the attractor. And there is a line, which is here, which is called a separatrix, which separates the basing of attraction of species 1 and species 2. So each one has a basis of attraction. So this is an example of a system which already exhibit a kind of bistable behavior. You can go to fixed point 1 or fixed point 2, right? Depending on the initial conditions. So each one has a basis for attraction. Then the good answer, the good question that you could say, okay, nice, I fully agree. Now I want you to give me a better description of the basis of attraction by giving me the equation or the solution for the separatrix. In our case, it's not solvable. Okay? It's only solvable if U12 is equal to U21, in which this case this is just a line. Okay? Yeah. Sure, you can do it numerically. I'm saying that there is no analytical solution for the problem, but for the full problem, but you can do it numerically. And actually, this is not very difficult because you can integrate back in time, and then what is unstable, because this is a line of unstable points, okay? If you sit here, go to this side, you go here. If you sit here, go perturb to this side, you go here. Therefore, this is a line of unstable points. But if you reverse the time axis, time goes back in time, what was stable becomes unstable, and what is unstable becomes stable, and then you can integrate back in time and get this numerically. Okay? So it's not a problem getting this numerically. In practice, if you have a problem like that in your projects and so on, you can do this. You can ask out the monitors. They will show you how to do this, how to find it. But you cannot calculate an expression for the separatrix in this case. Okay? So then you have, but anyhow, this means that depending on the initial conditions, either species 1 or species 2 will prevail at the end. There will be no coexistence. There will be elimination. But it depends on the initial conditions. So if you look this more or less intuitively, if you go to this part here of the phase plane, means that U2 it's bigger than U1. This part here, it's not exactly big. The correct assumption is not that U2 is bigger than U1, then you will necessarily get a U2 prevailing. But intuitively, if you look here, if I have a large amount of U2 and a small amount of U1, then you get U2 eliminating U1, and on this side is vice versa. Yeah. Yeah, I mean, the evolution over time will give you, here in this case, they will go to their carrying capacities. But I mean, you can put the mathematical problem, or just make an experiment and say the carrying capacity here of U2 of species 2 is a certain amount, and I go there and I put twice the amount of the guys. Well, they will go on, and then at the end of the day will be only the carrying capacity. But I mean, you can artificially put an initial condition that is it's not prohibited to have more. They will tend to the carrying capacity. So this is the this is the fixed point where U12 is smaller than 1, U2 is larger than 1, which means that the influence of species 2 on species 1 is weak, and the influence of species 1 on species 2 is strong. Therefore, the species 1 eliminates species 2, and you get elimination of species 2. And then you have the other situation is just a change in the names 1 per 2, and it's symmetric. Okay. So at the end of the day, what you get is that depending on the strength of the competitive interaction, you can translate the results if U12 is bigger than 1, then means that species 2 is a strong competitor for the resources, and here is vice versa. And this is rephased as competition is weak, then we can have coexistence. Competition is mutually strong. You have always elimination, and you get no coexistence. But the species that will prevail at the end, it depends on the initial conditions. And if the competition is strong for one species, on the other one, the influence is strong and the other one is weak, then you have always elimination of one species in favor of the other. Right? So this is the basic of this called the competitive exclusion principle, which says that species that have strong competition never coexist. Now, yeah. No, regardless of competition, no. No, the fixed point always depends. I mean, you have the stability of the fixed points depends on always on the A's. Yeah, come on, let's go back here. So say this one, okay? So this is stable only if these inequalities are, which are, these are solutions, but I'm not saying anything about the stability of them. I only observe stable solutions. Therefore, I have to go for the stability analysis, which I skipped here, okay? Without stability analysis, I would just end here. It's called a non-generic case, because this would be the fine-tuning of the constant, which is something that is unlikely to see in nature, okay? So you want results that are valid, if not for all values of A, at least ranges of values of your parameters. If you get a solution, and this is not only here, maybe you have some model, and if the parameters match exactly a certain condition, then I get a solution, whatever. This is a non-generic case. Means that this never happens in nature because all the parameters also are not exact. Therefore, it's not never exactly 1.000. Something, always something different, okay? So, okay, before going for the experiment, let me notice something. Here are the equations. Yeah? They depend on U12, U21, and on rho. Rho, remember, recall, that is just this ratio. But the stability analysis, rho disappeared. Okay? Disappeared. Why? Because I've just put the equations equal to 0 and rho was just multiplying the equation, so mathematically it's obvious. But then you can ask, okay, is rho, the ratio between the ratio between the growth rates of both species completely unimportant for the stability, for the exclusion or coexistence? So what do you think? Exactly. This line depends on rho. This line depends on rho when you have this. And also something else. Here we are doing stability analysis, and I'm saying, and this is, you have to believe that the stability of the fixed points is, there's a large basin of attraction, or it's global, okay? So I didn't show you that certain fixed points are global attractors. Yeah, you have to use theorems and so on. So, I mean, I'm assuming that if the fixed point is there, if you have only one fixed point, it's this global attractor, okay? So, but this is the situation at large times. Now, how long does it take to attain the fixed point or to be very close to the fixed point? This depends on the dynamics, and we didn't analyze the dynamics. We didn't show you the solutions. We have just analyzed the fixed points, and how long it takes depends on rho, because rho is connected to the time scales, and how long will it take to attain the fixed point, then it will depend on rho. Okay? Then you can do a lot of mathematics and analysis, like saying rho is very large, rho is very small. Then I can get a lot of results and so on. I can play with the equation if you want. Okay? So, but for our discussion, what now mean, we'll get a little bit more biological discussion, is that this results is connected to this competitive exclusion principle. You know, you'd say, why do you call it a principle? Isn't it just a result? No. What Gauss did, so Gauss is a Russian biologist, and he was interested in competition and so on. And so for the small story, where did he go to learn about competition and so on? To US and the lab of Raymond Pearl, guy which was the center of everything at that time, without having really found actually something very important that has his name, but everybody went there and actually got very good ideas. So that's the case of Gauss. And so he formulated the competitive exclusion principle as the stronger competitor always eliminates the weaker competitor. There's no coexistence. So this is not exactly the result as we have, because we have coexistence sometimes. So, but he went on and tried to show this, okay? So, in order to show this, he went to experiments with some protozoa. It's a group of protozoa called Paramecia. And well, this is textbook and things of, if you go from biology and 101, ecology 101, maybe you will find this, or maybe not 101. But, so he performed experiments with them. So he considered two of them, Paramecium aurelia and Paramecium caudatum, and he grew them initially separately. And he found a logistic type. I mean, this is grown in a culture, and he found a logistic type of growth when they are separated. Okay, so and then he made them compete. So the results will be like that. This is, you know, this is old style thing from the 30s, okay? So the people didn't have computers. There were no computers. You had to put the data by hand on your plot, okay? So, so you'd say he made the experiments of like, I don't know, this how 15 days or something. So you have the growth of the Paramecium aurelia up to something which seems to be more or less stable. And this is Paramecium caudatum, and also grows and goes to something which seems to be more or less stable. Okay, so very nice illustration of logistic growth in the lab. Remember, in the first class I showed you data about logistic growth with sheep in Tasmania in the field. Okay, was oscillating, and you say, okay, you really have to make an effort to say that this is okay for the model. But here you have something very with microorganisms, much better to make experiments. And then he made them compete, and what happened is that Paramecia aurelia outcompetes Paramecium caudatum, and caudatum goes away. Okay? Goes away. So this is exclusion, and obviously this has, if this principle is valid, This has a very important consequences. But this would be natural selection. Right? Principle of natural selection would be, if I'm a better competitor, you are damned. You will disappear. So, but, well, things are much more complicated than that. But here's a second example, which is more or less the same. This is the Argentinian ant that has been introduced to California, in California. So there's a different kinds. This is the humile and this is the Californicus. And actually, the introduction of the Argentina ant in California had the effect to exclude the Californian ant. And you have a kind of plot here of the dynamics of the process. So this is the situation without, when the Argentina ant was introduced, and then you have the decline of the Californian ant, and this is the Argentinian ant excludes the Californian one. That's an example of the thing. Actually, this is a very nice example, or a very nice situation where they actually could plot the extent where you had this. That's an invasion. That's a biological invasion, and obviously this is not instantaneous. And then what you have is the progression over space, and you see a wave of invasion and so on. It's very nice. So, but now, if we stick to Gauss, competition will always lead to exclusion, then you would say, if exclusion is the rule, why are there so many species? That's the point. Why are there so many species? So this can be illustrated by the paradox of the plankton. So there are, so you are already familiar with phytoplankton, zooplankton. Everything has been discussed here in the first day. Many groups know phytoplankton. It's kind of already a friend of you. So, so I don't need to explain much about this. But the point is, the phytoplankton is a primary producer, which means that it comes from light plus inorganic molecules or elements, okay? So, but I mean, what goes in the inorganic molecules? It's very few. It's nitrogen, it's carbon, it's, I don't know, phosphorus. So there are only few, okay? Like 5 or 6 elements. So you have 5 or 6 resources and light. So you would expect actually to say, well, with 6 elements, 6 inorganic elements, you would expect to have maybe 6 kinds of phytoplankton. Because you would say, okay, this one is a specialist on this element, and he therefore is very good in consuming it, the other ones can't. Then the other ones, and then you could have some overlap, if not 6, maybe 60, whatever, okay, of this order of magnitude. But there are thousands. There are thousands, okay? So how come there is no competitive exclusion? Why? Why do species coexist? You expected them to compete, and then we should be competing strongly, okay? So you could always argue, no, there's a lot, because never competition is strong, it's always weak, but this is not very good, because this is relying too much on this model. There are better models, and if you do a better model, which would be a model that takes species 1, species 2, and one resource. And now you have 3 equations, and you don't put any competition term between 1 and 2. They only compete through the resource. Therefore, they have some consumption rate of the resources and so on, and the resource also has a growth rate, a lot of parameters around, a hell of parameters, hello, but anyhow. What you will get is always that in this case, with 1 resource and two species, there's always elimination. There's no way of having coexistence. 1 resource, 2 species, no coexistence. Well, then you do the same exercise with two competitors and 2 resources. Okay? There can be a coexistence. There can be elimination, but there can be also coexistence. So the result of modern theory for competition, but if it's called consumer resource dynamics, it would be like if I have n kinds of resources, then I can have at most n times n species. Okay? That's the result, coexistence. But, yeah, but, you know, reality is sometimes cruel with theory. So why are there so many species? So maybe you can tell me. Give me, so let me speculate. Why is there coexistence? Because here we have a lot of assumptions that we didn't consider neither space, neither time variation of parameter, a lot of things. So maybe you can give me some ideas. Why is there coexistence? So unstable environment, fluctuating environment, okay? Could be, not always, right? Because depends on if the fluctuation is random and it's not too strong and so on. At the end, the fluctuation will cancel out and get the previous result. It's kind of intermediate perturbance thing. Yeah.
Maybe different combinations of resources are different ecological conditions.
So, yeah, one possibility is not is that they have combination of the resources, and actually one species does not may consume a combination of the resources. But anyhow, this will give you, if I have n, at most n square combinations of 2, or it will not change the magnitude completely, okay? But yeah, niches. The ideas of niches is like that. I mean, there are many vital resources, and maybe you have a niche where exactly this combination favors a certain species, and then there's this species is prevailing there, okay? But still, this doesn't seem to be able to give account for the orders of magnitude of differences. I don't think so. But anyhow, this is, the primary resources would still be very limited. Yeah, then so this would be the hypothesis of actually there's no strong competition because there are so many resources. Okay, that's it. It's richness. There is space for competition. There's so many resources. Okay? Well, consumer resource theory would say, nevertheless, there will be elimination, but it just will take longer time. Because, yeah, they have satiation, but I mean, if you have a certain number of resources, you have one species, say it's better competitor, it will grow. And grow away. Okay? So, at the end, you expect the competition to be important because one species will grow and so on. Okay? You. okay, you can, but this is a mathematical argument in the sense that maybe these equations, okay? But what I'm saying is exclusion principle is not relying on the equations. I mean, you have theory, obviously, but you have also experience like Gauss and others. I mean, Gauss is old, but that you would expect no coexistence. Maybe the species are regulated by resources, but also by predators, and that could give you a regulation of coexistence. Sure, one of the famous cases, it's even simpler. It's, I have my resource, and I have consumer 1, and I have consumer 2. Using basic theory, you'd say one of them outcompetes the other one. Let's say that this one is the strong guy, okay? C1 would outcompete C2. But it may happen that C2 is able to predate C1. It's called intra-guild predation. Intra-guild means that these two are guild because they consume the same resource. So maybe the weakness of the competitive weakness of C2 can be compensated by the fact that it predates C1. And this can give you a situation of stability, of coexistence. And you can have predate, then you have this, can have this C1, C2, resource, predator, like that. All of these things are called community modulars, community moduli. Okay, so this is called the integral predation model. This is called the diamond model. So these things can be studied, and you can find situation of coexistence because there are more than 2 species. Okay? So one other thing that is a lot of people talk about, and it's one of the easiest, it's the effect of spatial dynamics. If environment is not completely homogeneous, there may be places where where one species has some extra advantage. Maybe the space is just too confined for the strong competitor to get there, and it loses the ability to compete. So heterogeneity, which means can also think about refugia, okay, for one species, for the weak competitor. So there can be an effect of the space on the thing. And then also networks, maybe we didn't analyze networks and so on, okay? It can be this kind of thing. But the point I want to make, and this is my last point here, is I have written a very basic equation which didn't even model the resource dynamics. And I got some conclusions that lead us to think that competitive exclusion should be the rule. And then you have Gauss things, and then you have consumer resource dynamics. All of this tends you to, with the simplest model, to say you should have exclusion. And actually, you see exclusion in the word. It has clearly, I showed you the Argentinian end excluding the other one. So then obviously you'd say, okay, then but why are there so many species where they are coexisting? I go there and I look at the situations where they are actually coexisting, okay? You can also say, for instance, maybe they are coexisting on a transient, but the transient is, I mean, century long. This would be case for plants, for instance. If the time for, say you have a forest, they have many trees, why is not there only one tree, the one that is the better competitor? Okay? Well, you could say, okay, but the time it takes for the better competitor to eliminate the other competitors is 1,000 years. And therefore, for observation on the scale of 1 or 10 years, it is as they are coexisting, because it's a long transient. Okay? So, but what is the importance of these simple models and the principle of competitive exclusion? And this is very nice. It's the construction of the theory in ecology, because with these results, you would expect elimination, but you see coexistence, and then you have to explain coexistence. Therefore, you always explain any coexistence. If you didn't have these results, and you didn't have the work of Gauss and arguments saying that there is natural selection and can happen through competitive exclusion, if you didn't have this, you would not ask a question about why are they coexisting. You say, okay, they are coexisting because they are coexisting. They are just friends. I don't know. Okay? So the question about coexistence only makes sense in the light of theory, which has been that has indicated that exclusion should be the rule. And when you see the coexistence, then you have to explain it. If you didn't have this theory and this arguments, you would not even try to explain why there's coexistence, because you just know species coexist. Why? Why shouldn't they not? Okay? So that's important, and this is the main importance of this models and this discussion. It is not that that we really expect to validate models simple as these ones. Okay, that's not the case. But the theoretical discussion is such that it implicates that you expect something in nature, and when you don't see it, you have to explain why you don't see it. Okay? And this actually created a lot of new theory. All the niche theory comes from that. Lots of things. The ecology of the 60s to the 80s or 90s, very much influenced by these discussions. The names are important names of these discussions is Hutchinson, who has a paper called The Paradox of the Plankton, and then another one that discusses more or less the same thing, which is it's a conference, and the paper is called Final Comments. But anyhow, it's about that. And developing the idea of niche and so on and so on. If you go for Hutchinson, then you will have very nice things. And MacArthur, which is also very important ecologist and mathematicians, actually. Okay, and so the Hutchinson is this guy here, yeah, here. So this is the book, but if you Google GE, which is George Evelyn Hutchinson, if you Google this, you will find paper of historical interest, but discuss exactly this. And moreover, Hutchinson writes in a so charming way that it's really nice and delightful to read the papers of, and it's not very technical. I mean, it's technical, yes, but I mean, he knows how to. He was a, very famous professor. So that's it. So, what we would expect for your afternoon or for your group work is we are in day 3. I would expect that you already have some equations and analyze them, yeah, because you have 6 days. Right? You are in the middle of your journey, and well, you better try to focus on. I expect you to know at this point which is the important biological effects that have to go into your models. You expect you that you have more or less decided what the questions you are asking about your system, and what should go into the equations. And maybe many of you have already equations, and most probably today is the big day of destruction of equations. Okay? You have probably some very simple models, and Most of the time, in D3, you just say, oh, it's too simple, and there comes a monitor and kills it completely, and something like that. So this is normal. You still have a lot of days, okay? And but we expect you, at least they have taken some strategic decisions about the model, and while trying to write and not just writing the equation and analyzing them. The way you find it better, it's usually for the models that you will be working, it's probably by numerical integration, which you learned yesterday. Right? So we have no 6 o'clock activity today. You just work and then you go. I mean, if you want to stay, you can also stay. Okay? That's it. Okay? Thank you.